Today we're going to talk about the sequencer, the Christmas tree, the thermal disc time delay relay. There's lots of names for this part. However, if you're going to order it, you want to know its true name, which is a thermal disc time delay relay. It is a mouthful. Most people understand sequencer. There's many types of sequencers out there. There's one pole, there's two pole, and then there's some that are adjacent to other ones that even add even more poles to it, all single throw. We're going to go over those today. On the smart board, we're going to wire a motor up to it, a light bulb up to it, and we're going to talk about it at the Cantex box, so stay tuned. Today we're going to talk about the thermal disc time delay relay, also known as a sequencer. It's got lots of nicknames. People have called it a Christmas tree because of its shape. What's important about this is it allows us to have a little bit of on delay and off delay. It's a nice integration before going to circuit boards which have that integrated into them. This doesn't require 24 volts to be present at all times to have that delay. Hence why it's called a thermal disc time delay relay. So when we apply 24 volts to the dark colored brass connectors down here, then that resistance, it warms up and it causes the plate inside that little disc to rise because of the temperature. And as it heats up, it starts to bridge a connection between the pole, the line to the load side. It doesn't matter which side you go, line and load. I can show you as an example on this. But we have the first pole, okay, which is the middle section. Then we go up to the last pole, the final pole, which is up top. So this is a single throw because it only goes in one direction, okay, but it is a two pole. So this is a double pole, single throw, time delay relay. So it's very good. If we wanted to use this as a blower relay to control our blower, many manufacturers have done it. As an example, it's been used in Goodman for a very long time. What they were trying to do is get as much efficiency out of their evaporator coils as possible. If we can let that blower just kind of not come on immediately, then we can allow so much liquid refrigerant to flood the evaporator coil, making it nice and frosty cold. Then when that fan finally comes on within about 12 to 15 seconds or whatnot, it's more comfortable. So we're controlling comfort that way, and we're getting that scientifically by dropping humidity. So we're collecting more moisture on that coil, right in that beginning process. Same thinking was done when it was shutting off. It had to cool down before it would open up. So I'm going to show you how that works. There's no diagram on this that tells you if it's if you're on the contact side or the coil side, so I'm going to show you how to tell the difference there. Another reason why I like these, if you can remember, you always have a dark colored brass connector, which is the low voltage side. Pretty much, if you can remember that, it's kind of hard to mess it up. We have a live L1, L2 like you have in the field. It's 220. We have a T1, T2, which is the load side. Our goal is to try to get L1 and L2 up here to T1 and T2 so our load can operate. This load is just a 120 volt light bulb. However, in the Cantex box we have transformers and contactors, so you'll hear a clicking noise. And when you hear that clicking noise, that's just the contactor engaging, bringing our load on. We have R and C, which is our 24 volt secondary control voltage, which we're going to utilize to control our relay. So we're going to go ahead and just demonstrate the power first. We'll come up to R and C, and you should see that we have 28 volts. And then we'll come over to L1 and L2, which you should see we have 243 volts. Obviously, T1 and T2 is going to have absolutely nothing, no matter what the combination, because we don't have a full two legs of power. I'm going to go ahead and demonstrate the light coming on first without a relay. We're going to go ahead and run L2 up to T2. And then we're going to wire L1 up to T1. And you'll notice that when I do this, you'll hear a clicking noise. That's the contactor making that noise inside the box. And as long as we have both legs of power present, then the load will energize. So what we're going to do is we're going to go ahead and run one of these legs of power through our relay. So I'm going to go ahead and just take the T1 side. And we have 2 poles here, so I'm going to demonstrate this on both poles. We're going to go to the middle pole, okay, which is the first pole. And tell you what, I'm going to do this a little bit differently. Get picky on my colors. I'm going to go ahead and take yellow, and since I'm not breaking anything, and I only have 1 yellow, we're just going to leave it like that. There's 1 leg complete. And I'll take my 2 black wires, and we'll break those across the relay. So here's L1. We'll come over to our first pole. We'll come out of our first pole. And come up to T1. And that's all we have to do on the high voltage side. And we're going to apply 24 volts to this. Trying to get a good connection. I have to be careful because there's live power here. The last thing I want to do is make a mistake and touch something, because that's not a blooper that I'll enjoy providing. We're going to go ahead and come over to here on the other side, and as soon as I apply the 24 volts, you'll see the light come on here in a few seconds. And as you see, that took a while. That's why it's called thermal disc. The disc had to warm up. Now, here's what's cool about it. If that coil was nice and frosty cold, you saw how we got a little bit more comfort when that blower first came on, if this is being utilized in theory as our blower. Now, when we lose the G call, because we're going to be wiring it up for a fan motor, blower motor, it still runs. Matter of fact, let's go ahead and remove all these low voltage wires. It is still running. That thermal disc has to cool down. It has to cool down. And so it's slowly cooling down, and once it cools down to a point, it'll break contact, and the load will lose 1 leg of power, and it can't run. And there we go. And so we're going to demonstrate that again, but we're going to do it on the top pole. Okay. And now we don't make across this way. We actually make across the entire relay. So this is the proper way to wire this. So please take note of that. We're going to go ahead and hook up our coil voltage. Be carefully get in here. It's one of the harder relays to do with live power, and try not to brush your knuckles past one of these bolts that have a full leg of power on it. I'm going to come up here to red, and we'll let the relay warm up again. And it was a little bit quicker on that side. So now we're going to go ahead and remove the 24 volts. And as you can see, the relay is starting to cool down, and eventually it will turn itself off. Anytime you wait on this stuff, it never does it too fast. But so we lost a G call, and so much time went by, and with that time passing by, we wound up getting more efficiency out of that evaporator coil. And that's why they use these relays for blower motors. They're really good relays for blower motors. So I'm going to show you how to do this one more time, but this time I'm going to calculate what that time is. Even though you can watch this video and you can see how many seconds it takes to warm up or cool down for off, I'd like to know myself. And so we can look at consistency. One thing I want to go over with you is when these things stick, you want to know how long, if I remove 24 volts, should that relay stay engaged? Because when these relays typically fail, they fail in the closed position, which means the load does not shut off. Sometimes they do fail in the open position where the load doesn't come on. But if you're using this relay for a set of heat strips, you may experience your heat strips running if the relay has failed in the closed position, the sticking there. You may experience your heat strips running, and if you're trying to cool with that, you're not going to get a very good temperature split across your air handler, not just your evap coil, but the entire air handler, because as you remove 20 degrees of heat going across your coil, you're going to warm that air back up about 10 or 15 degrees, and you'll see like a 7 or 8 or 10 degree split on your air handler this spring. It'll be because maybe one of these is being used as your heat strips, and sometimes they just stick. And sometimes you can just thump them a couple times and they'll unstick. Anyways, if you ever get one freed up, just replace it. It's going to keep messing up. They're not that expensive, and they're a really good relay of choice. We'll cover all that. Let me go ahead and find out what roughly time frame should we be looking at for this thing to warm up and turn on, and then cool down to turn off. All right, so we're going to wire this up one more time. I'm going to go ahead and hook up my common. And then we're going to hook up the 24 volt side. And now I have my timer here. And the moment we connect this, I'm going to go ahead and hit start. Okay. And now we can see together how long does it take for this load to come on. That was about 11 seconds. All right, so now I'm going to de-energize it. We're going to go ahead and reset that, and we're going to see that one more time. How long it takes to turn off. And there we go, 30 seconds off. So let's try the other pole, which is right below it. We're going to come down here to the middle pole. And we're going to do the same thing. And go ahead and reset. And the moment I apply 24 volts, I'm going to hit start. And we're going to see if one's faster than the other. That was a little quicker. That one was 6 seconds. All right, we'll go ahead and reset it. We'll go ahead and de-energize it. And that was 32 seconds. We're going to try this one more time. And what I'm looking for is consistency. Now, anytime I have a feeling that these are sticking, I always do this, because you might get one that takes 1.5 minutes to cool down. Now, you know that if the average is 30 seconds on off delay, then why would it take longer than a minute? You know, that's a very fair amount of time, 45 seconds to a minute. If you're taking longer than a minute to cool down, change the relay out, because chances are it's sticking when you're not there. So we're going to try this again. First time was 6 seconds. It looked like that was consistent. That was very consistent. Let's see if it's consistent with off time. Try it again. Oops. Let me reset that. And go. So it was 32 seconds the last off cycle. Let's see if we can get 32 seconds again. So as you can see, that was 38 seconds. So there's not a whole lot of consistency there. But still, like I said, if it's a minute, you know, that's a long time. Let's try the top pole. And now I know as we exercise, this thing is heating up and cooling down, heating up and cooling down. But it doesn't matter. We should still be getting consistency. It's a working load. We're going to go ahead and reset. And we're going to apply 24 volts, and we're going to measure our on time again. I think the first time it was 12 seconds when we went across this very top pole. We had consistency on the middle pole where it was like 6 or 7 seconds each time we did our on delay. Let's see if we get 12 seconds on this on delay again. And go. Seven seconds. So it was 5 seconds faster. Seems like 7 seconds is now the on time. The very first time it took 12 seconds, or the first time that we actually recorded it. And so now we're going to release power, and I'm going to see if it takes 30 seconds to drop this out. And go. "45 seconds. So, like I said, if you had one that was taking you more than a minute, replace it. I can almost feel the warmth on this relay. It's not hot, but I can almost feel the warmth on it. So that could also be it's taking longer for that area to cool down. There's a lot of heat trapped in there. And so maybe if it's off for a while, maybe its off time is really 30 seconds. But I can still get a lot of efficiency out of this thing. This is a really good relay. I'm going to go ahead and show you how I can tell if I have... matter of fact, let's just look and look what power would be. Let's just say I had 24 volts here, even though we all know that there's not 24 volts down here because we're not hooked up, because here's the other end of it. But let's say we did have 24 volts and the load wasn't happening. Is it a bad relay? Is the relay not making? Or is it a bad load? Because there's no ampacity, so is the load getting voltage? So how we would do that is we'll measure across the points. And if you notice, I have a measurement of L1 plus L2. So I know the relay is open because I'm reading 243 volts of electricity. Now, if you notice, when we apply 24 volts, we're going to wait about 7 seconds, I think. The relay should energize. There we go. That's about 7 seconds. At least it feels like it. Now, if we wanted to see what the power supply is, down here we read our 242. Up here, we read our 242. But if we look across here, we read 0 because it's the same leg of power. We can't read a difference on L1 to L1 because it's still L1. But if we were to remove power, and let's just say the relay's stuck in a closed position and the load won't shut off. You go to your relay. Hey, I'm reading 0 volts across it. Yeah, that's why my load's running. And as we know, 45 seconds of this, it'll shut off. And then I'll show you how we have L1 and L2 across there. And I'll explain why we have L1 plus L2. How do we go from 0 volts? I'm going to leave it there. How do we go from 0 volts to 242 volts? How does that happen? Come on, relay. Now we read 242 volts. If we look here, we have the black wire, which is L1 up to this point, right? But if we look over here, the yellow wire, we have L2 over to here. Well, through the load, I'm getting L2. So if I wanted to see voltage, for example, between L1 and L2, I have 242. Between T1 and T2, I have 0. Right? And if I wanted to see what my voltage is between T1 and here, it's going to be 0. 0. 0. 240. 240. That tells me that just really confirms that my relay is open. And there's nothing wrong with my load. Because if my load had a bad winding and the winding was open, then I would not be getting L2 here. So I have L1 plus L2 at this present time. So let's go ahead and take all these wires off. And what we're going to do is I'm going to show you the resistance, and I'm going to show you how I can tell if I have contact or coil. Now, like I said earlier, if you look, there's discolored terminals here. They're brass, and that's always going to be your coil side. If you just remember that, you're good. Let's see what we will have here if we come over to continuity. There's the ringtone with no numbers because there's no resistance. Just a ringtone. So we're looking for a ringtone. So this relay is open here and it's open here. It's a good relay so far. That's how I would test this relay. Okay, the relay's not stuck closed. Relay's not stuck closed. And then if I came over to here, down at the bottom, I should read numbers. And I'm reading 47.6. And now, so I know that the resistance a little higher on this. Once it warms up, it'll make contact. So now what I'm going to do is I'm going to take these two wires here, and I'm going to apply 24 volts to the bottom of this time delay relay. And I'm going to show you with contact There we go. We'll probably go to ringtone here because it's only 7 seconds. Here, see, now we have a relay that's good. And now both of these should ring out. See, they're both ringing out. Now, two different poles, so you don't have a ringtone on the same side. It makes across the relay. It makes across the relay. And so now I'm going to disconnect 24 volts. Still closed. It's still closed. Still closed. Still closed. Still closed. Okay. Boy, 30 seconds can be a long time when you're waiting on it. One of these will always shut off before the other one. Relay is still closed. All right, that one opened up, and they both actually opened up at the same time. And so there we go. There's nothing more to demonstrate on the Cantex box. I hope this helps out. If not, we hooked this up to 2 loads. On the next portion of the video, you're going to see how we used a light bulb to wire it to, giving it 120 volts. One of the legs is 120. So we ran one leg through here, out of here to a light bulb. We ran the same leg up here, out of here to a fan motor. And we're going to demonstrate that. Then we'll take it to the smart board. So stay tuned. All right, we're going to go ahead and demonstrate the same relay on the motor here. I've got a power supply now. We got it a little bit in frame, so you can see here between L1 and L2, I have 243 volts, and I have 24 volts down here as well, 27.5 volts. So we have live power. I'm going to wire 24 volts to the relay. I'm going to take both legs of power and energize this motor. This PSC motor is going to require both legs, L1 and L2, for it to run. We have the white wire here, which is one leg of power. The second leg of power is for the speed taps. Now I have 3 speed taps. I have blue, black, and red, which is low speed, medium speed, and high speed. And I'm going to demonstrate on this relay just 2 of these since I have connectors on them. Low is red and black is high speed. And then we have our light bulb here. Got a little vintage bulb here. And I have a path of electricity is going to be neutral. So this neutral here, all right, is wired to the back side of this light bulb through the wire that's got a wire nut on it. And the other side of the light bulb is wired up to the top side of this relay here. And so do we need to do this in the field? Probably not. However, we want to be very transparent and show you different ways. Now, since I don't have neutral here, I have a little extension cord here. I'm going to go ahead and plug in neutral. And just to kind of help you understand path of electricity, I'm going to show you now that I have 240, and if I come over to here, I have one leg of power, 120, and over here, one leg of power, 120, right? Now I'm going to show you that same path is neutral all the way through the bulb, and check this out. I have 120 here and 120 here. And if I were to disconnect my neutral wire, okay, I'm going to try that again. 7 volts, 7 volts. You see how I didn't get 120 and 120? It's simple. It's because I interrupted my path. So I'm going to plug this back in. I'm going to check my path. Now I have neutral again. And the same thing, how we have both legs of power present. I'm reading neutral as if it was a leg of power, because through the bulb, through this filament, I'm getting neutral. That's how that works. And so I'm going to come around the other side here, and I'm going to hook this thing up, and we're going to get this thing running. I'm going to leave this over here just in the event I want to use these leads so I don't have to reach across high voltage. All right, so we have neutral hooked up at this point, and the moment I put power on this, this will no longer be neutral. So I'm going to show you something very neat about that. Let's go ahead and take one wire, hook it up to one line. Now I told you this was neutral, but the moment I put power here, it's amazing I didn't short anything out. Now if I were to take power and put it on that side, we're going to see a lot of smoke, a little bit of spark, maybe the lights might even go out in the room. Most likely the television behind us or the smart board behind us will definitely go out because we're plugged into that for neutral. But because I gave it power, that path back across there, it energized the load, as it was supposed to. There you go. And that's what that is. So if I were to come up here and connect it to this side, once the relay warms up, it'll energize and provide this power, this leg of power over here, and the bulb will come on. And that's pretty easy. So what we're going to do is we're going to now take one speed, and the speed that I'm going to use is going to be the low speed, the red wire, and I'm just going to make a light connection, hopefully it stays on there, onto one side of the relay. We're going to take the other leg of power. Let's go ahead and use the black wire. A couple ways I can do this. I can come from down here and come up to here, or simply I can pigtail off the top side of this and come this way. It doesn't really matter. Let's see how I want to do this. Maybe what I'll do is I'll just run it down to the bolt. Might be easier to disconnect. And so now we have our loads wired up, and that's one leg of power. The other leg of power is going to go right here. Okay. So we're going to go ahead and supply that leg of power. Okay. And now everything that's between L1 and L2 has been wired up. Okay. The only thing that's required now is to energize the relay. Once we energize the relay, it'll warm up and it'll bring these loads on. And now that we have two loads here, what I want to demonstrate is which order the loads come on and come off, because we're running two poles. We couldn't do that over at the Cantex box. All right, so we're going to come over here very carefully and put common on the relay. And the only thing it's missing is 24 volts. And at this point in time, it's warming up. I think it was about 7 or 8 seconds or so that it needs. Okay, that took a long time, and I apologize for your delay there. Well, let's look and see what we have. We have one load that came on, but the second load, it did not come on. So let's go ahead and look at it. The moment I was going to get my meter out to see if we had 24 volts on that, it came on. Imagine that. So I would say that is a very long on time. Now I didn't have my stopwatch governing what that was. Maybe in the comment box you can share that with me. But I would say that was a little bit of a long time. So we're going to test this out and see if we have any issues with it. Let's go ahead and disconnect 24 volts. Both loads are going to run at the same time. There's our 24 volts. Okay, the fan motor shut off first, and then the light bulb shut off. Okay, so a little bit of delay time there. So let's go ahead and try this one more time. And I know we just warmed the relay up, and this is the first time this relay's had a little bit of action. So we're going to go ahead and measure the amount of time that it takes again. let's see if, just because it's a brand new one out of the box, maybe just need a little bit of action first. So the moment I engage this relay, we're to go ahead and test the amount of time that it takes for it to come on. And go. So at the Camtex box, our 2-pole thermal disk time delay relay took 7 seconds. And now it's taking longer to energize. Okay, the light bulb is hooked up to the very top pole. It came on in 30 seconds. 6 seconds later, the middle pole, the first pole, it made. All right, so now we're going to go ahead and hit stop, or reset, and we're going to go ahead and cool the relay down by removing 24 volts, and we're going to see how long it takes to break contact on both poles. Okay, 13 seconds on the off for the fan motor, 18 seconds for the off on the light. Interesting. No two relays are the same. They're thermal disk. As you can see, they're good, but as you can also see, they can be a little temperamental. Let's see here. I'm going to go ahead and switch some speeds. We're going to go ahead and disconnect the low and connect the high speed tap. There we go. I'm going to show you something pretty cool here too. Why not? I don't want to confuse anybody. My goal is to teach you, not confuse you. But as I said, there is neutral present here because of the path of electricity until we apply power, and then it comes on. All right? And I've also showed you that there is high voltage present on these motors, even when they're not getting 2 voltage or 240 volts. I want to show you something pretty neat. Let's go ahead and put the backlight on, and let me show you that if I go between this pole here and the top pole, you should read 120 in theory. And we have 120. Imagine that. Now, how am I getting 120 there? It's simple. Because this, and I'll show you here, if I touch here and here, I'll have 120. But if I touch on this bottom one, I'll have 0. It's the same leg of power. But if I touch up here, I have 120. Beautiful, isn't it? And if I also go across the switch, you'll see that I have 120. Imagine that. And if I go across the bottom here, you'll see I have 240. Now, I'm not trying to confuse you. It's because one load is I'm using one leg of power to neutral. You have to understand your path of electricity. I was not trying to confuse you, but that is just really cool stuff. And so I wanted to show you the reason why I can't hook the light bulb in the motor up to the same pole is because if I did that, I will be providing 120 to my light, even though the motor doesn't have 120 to come on. I will prove that to you. If I did that, if I touched here, the motor will run. If I touch here, the light will come on. Imagine that. Pretty cool stuff, huh? Respect your power, understand it, and stay safe with it. So let's go ahead, and we've already reset the clock. We're going to apply 24 volts to our relay. We're going to see if we have any issues now, on and off. And remember, we're running high speed this time. And go. See which one comes on, the fan motor or the light bulb. The light bulb comes on. 38 seconds. "45 seconds later, the blower motor comes on." So there would be your on delay. We're going to go ahead and reset this, and we're going to go ahead and remove the power, and we're going to calculate the off time. And go. Motor shut off in 13 seconds. And the light shut off in around 18 or 19 seconds. Well, there you have it. All right, we're going to take the rest of this lesson over to the smart board where I show you how to wire this up step by step. And we're going to talk about voltage again between L1 and L2 and where power is always present. Stay tuned. All right, that was some pretty neat stuff, wasn't it? I love messing with neutrals and 120 loads while we're messing with the 240 volt loads. I just think it's really cool to teach that part of it. These lessons get more advanced as we go on, so please subscribe to the channel, keep up with it. It's a big deal. Share this with others. I'm always trying to release something that is going to help somebody in this field. You may not need to understand the relay itself or what practical use we're explaining in the video, but possibly maybe there's something else, like maybe the path of electricity you may be able to get out of that, because we cover so much. Also, we understand our history, and we talk about that. We talk about the timelines. Behind me, we have a timeline here, and I just put it in about a 30-year span. Of course, it goes a lot further back than that. However, the technology doesn't really change. So, we wanted to talk about, hey, 10-year increments, what did we pretty much see change in our industry? And because there's still equipment out there that is being serviced, there's equipment that's still 80s and 90s. They're still running. There's also equipment that's running right now with a lot more advanced technology and a lot less components. So understanding their timeline and understanding how to work on this older stuff gives us the ability to be better technicians, to better understand the purpose of a good truck stock, and better understand the purpose of supporting the team by having what you need and getting your customers up and running, by making sure that you're aware of yesterday so you understand today better and know where we're going tomorrow. The industry is going to constantly evolve, and at the end of the day, the components don't get complicated. I think what gets complicated is our ability to comprehend. We see so many changes within our industry, we don't know why. And understanding why and the manufacturer's intentions will better help you understand why. So why do we go to the ECM? A lot of people don't know why. It's easier to understand this once you understand why. I have the relay of choice today, the thermal disk time delay relay, the sequencer, or Christmas tree. And we have a run capacitor PSC motor, and we use those three components in the middle of our video to show you how we chose to wire up two different speeds on our PSC motor. Once we leave this relay, okay, if we want to stay with a on delay or an off delay, we're going to have to go to a control board. That's what these control boards do. Plus, they've integrated the fuses into them and whatnot. And we're going to go over those soon. So we're almost there. And as we progress through our timeline, you'll see that we lose components. Eventually we get down to where everything's just integrated right into the back of that motor, up in the module section. Getting right into it, we have L1, L2. We have our motor, capacitor, or time delay, thermal disk time delay relay, our low voltage terminal block, and our 24 volt Honeywell thermostat. And so we're going to wire this up, and I've color coded things for you because I want to make sure that we always practice safety. I'll always give safety tips too. L1 and L2. Notice one is red and one is black. Well, if you look at my motor windings, I've labeled red and black. I wanted to distinguish, not that common has to be L2, Not that run and start have to be L1. What I wanted to distinguish is that run and start are always on the same leg of power. That's what we need to get out of that. And so if I wanted to rewrite this, then these would have to be black, that would have to be red, and I don't have to change anything here, but if I wanted to, sure, why not? So that's just, as long as run and start are on the same leg of power, you're good. And I also talk about, you know, when we're wiring this up, you're not doing it here. I mean, maybe you're writing it on a napkin or something, giving it to your apprentice that you're teaching and saying, here, have fun with this. You know, you're going to the call, we're going to put a motor in, wire it up. And here's what he's doing. He's above his head, he's working. Can't really see. Bunch of wires in the way. He sees red wires 100 times. He doesn't know if those red wires are high voltage. He doesn't know if those red wires are low voltage. They're just a bunch of red wires. Same way with the black wires. Same way with the white wires. They're all over the place. And they're zip tied to make it worse. And then schematics, because it's in a dark, cold, moist environment, they happen to be covered in mildew. And or torn off, faded, right? And so real world application is you need to understand your path of electricity. You need to understand your L1, your L2, your 24 volts. And you need to understand, how do I safely wire this up without causing extra work or creating a harmful work environment? So my tip for you is start with one leg, the high voltage side, complete it all the way through. Then go to your next leg, complete it all the way through. And as you do these, you want to inspect it to make sure nothing's questionable, all right? And then when you're done, then work on the low voltage. Never work on one leg, then low voltage, back to the other leg. You don't want to go from one component at a time. That's not good practice. You want to go one leg at a time. And when you do that, all those wires that happen to be red, or all those wires that happen to be black, you now know that, no, I hooked all the black wires up. They happen to be high voltage. What about those other black wires? Well, they're not high voltage. Well, how do you know that? Oh, because I traced them out, and I know for a fact it's low voltage. And that's how you do that. But if you're just trying to get the whole thing done and you're in a hurry, that's a very bad, poor frame of mind, and you want to break those habits. All right, so as we wire this up, as I told you, we will stay high voltage first. We will work our way across each leg, and then we'll finally get to low voltage. Getting right on into it. Okay, we're going to go ahead and take L2. Let me go ahead and get the right, there we go. All right. We're going to take L2. We're going to go ahead and land it first on the transformer. Doesn't matter which order you do it in. I'm just picking transformer because in my image, that is the closest high voltage load that I have here. My relay, I have two poles here. I have pole number 1, and then I have pole number 2. Now, it doesn't mean one's L1, L2, right? But they don't make across this way, right? They don't do that. That's not how these work. All right, so what they do is they make across. They make, actually I'm going to do this one in red because as I draw it across, the relay is going to be very hard to see. They make across, okay? And that's how that works. So I can pick one pole. That's all I need is one pole. Now I showed you multiple poles earlier in the video. I wired a light bulb and I wired also a fan motor. Matter of fact, let me look at something for a second here. Let's count images. How many images do I have? Okay, so I use that as one image. So 1, 2, 3, 4, 5, 6, 7, and that's an image. think we can do 8 images total. Okay. I'm going to see if we can't do a light bulb here to make this a little bit interesting. All right, give me 1 second. All right, so now we have a light bulb. I went ahead and wired the neutral block to it. And now we're going to pretty much do what we did on the motor. So let's see here. We want to take L2 now, and I can come down to this middle pole, doesn't matter which one. I'm going to come out of the middle pole on the other side. We're going to land it up on the common side of the motor. And that's pretty much all that has to happen to L2. We can also run L2 again. We can land it right here, and then it's open out of the top pole. We can come out and we can run it over to the light bulb. And the moment we bridge a connection over to here, this load will come on. And so we have right now L2 present here, L2 present here, and that's it. Now, even though everything else is wired up, I have L2 present here too, by the way. Everything else is wired up to have L2 energize it, but L2 is not present, not until L2 becomes present. Where L2 is present is where we will measure L2. We'll measure L2 here, 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 and here. We won't measure it here, here, and here yet. And so we're going to go ahead and wire up L1. We're going to come out. We're going to come over, land it on the transformer. We'll go ahead and label that while we're at it. We have L1. We're going to come down and we're going to run power to our run winding. We're going to go ahead and label that L1. And we're going to come around and land power on our run capacitor. We're going to go ahead and label that L1. And then out of our run capacitor, we're going to come out and we're going to land power on the start winding, and we'll go ahead and label that L1. Now, even now we can't label this L2. And the reason why is because at this present time, this is L1, which means we're going to backfeed power to here, which means this is L1. Now, here's what's interesting. What I was trying to show you at the light bulb, what color should I use? I'm going to pick a color. I'm going to go ahead and use purple because there's nowhere else on here. Oops. Believe it or not, that's neutral right now because of the path of neutral through the bulb, okay, back to here is neutral. So we have L2 in neutral, L2 and L1. And let me go ahead and label this one. This is L1 here. And so that's presently right now, at this present time, this is what this, because of path of electricity, this is what power we will read at this present time because our relay is reading open. So now we're going to go ahead and run power to our transformer, or off of our transformer, excuse me. We're going to say we have 24 volts coming over to our terminal block. Out of our terminal block, we come over and we feed 24 volts to our base plate of our thermostat. Through the thermostat faceplate, it sends power through the base plate, and then we'll get back to the transformer, and there's our loop energizing our thermostat, and then we'll start toggling all of our other terminals. For example, we'll have 24 volts on O when we get a contact for cool. We'll have 24 volts on Y when we get a contact for heat, and between contact for Y on a heat pump with O will be in cool mode. If it's a straight cool air conditioner, then Y will not be contact voltage for heat. It's contact voltage only for cool. But as you see here, I have an O here. As we get into other videos and we start talking about multiple speeds on our motor, like variable speeds and whatnot, these other 24 volts on this terminal block, they are going to come to light where they're very important, because we're going to have to ramp up or ramp down the motor based on what call we're getting from the stack. In this case, it's very standard. So the only call we're concerned about is a G call to be wired to that blower relay. We're calling it a blower relay because the relay is used for the blower. So we're going to go ahead and change the colors up. And we're going to say the thermostat will provide a G call for the fan to come on no matter what other contact voltage is sending out for cooling or for AC, for heat, whatever. I know I don't have a heat strip or a W terminal. It's irrelevant. Our focus is really just this relay. We don't even need to put the light bulb in here, but we're just trying to have fun with this. It might be too much for you. Maybe it's not enough for you. We want to keep our viewers engaged with learning. So we're going to go ahead and run 24 volts now. I'm going to come around the right hand side of this and of this relay. We're going to put 24 volts right there, and we're going to now provide common back to the transformer. There we go. And yeah, it looks pretty messy, just like it does inside your air handler. So now we have a loop, and at this present time, we have 24 volts there. So what's going to change? Well, this path now stops. Let's look and see what else stops. No longer is there going to be neutral present the moment that relay closes, and no longer is this going to be L1. So what we're going to see once this relay, once we heat up and the thermal disk makes across these two poles, we'll see L2 present here, L2 present here, and we'll see L2 present here. And now that our motor has 240, this motor will run. And now that our light bulb has 120 volts, you know, one leg of power over to here with a path back on neutral, the light will come on. And as we remove 24 volts and the relay cools down, these will drop out independently. And that's pretty much what we showed you with the blower motor demonstration with these two loads. That's really all there is to talk about here. Rewind it as many times as possible. Share this with others. Share it with your whole service team. Hopefully you got something out of this. Practical use, unpractical use, just understanding path of electricity, understanding the relay itself. Feeling confident, feeling more confident about the other relays that are on the truck that need to be there, other relays that are in the parts room. One relay that you may be looking for, maybe you can't find that exact relay, but you understand other relays, so those other relays could help you just as well. Any relay that's normally open can be used for a blower motor because the ampacity is not that high. You can't use it for a compressor now, but you can definitely use it for a blower motor. You know, like these videos, that helps support our algorithm, and obviously we want you to subscribe. Please subscribe because that supports your channel the most, and we love our subscribers. Leave a comment in the box. We'll read that. We'll see how we can contribute any of those to our next videos if we feel that's applicable. Thanks. Stay safe and stay tuned.